Roman numeral 4, formulas of ionic solids. Let's remember that ionic solids are held together by electrostatic forces, and electrostatic is just going to be another way of referring to the attraction between oppositely charged ions. And these oppositely charged ions, and one way of thinking about the electrostatic forces is that the charges must always balance, they must always cancel. So the positive and negative charges must always cancel. Okay, and that's one of the things that leads us to the formulas of ionic solids that we'll see on the next page. And what I'll do is, so they must always cancel out in the formula. And I'm going to start over here with some examples. And the examples are going to be looking at things like, well, if you take a magnesium ion and you pair it with a fluoride ion, then the question is going to be, what's the formula for the ionic compound? And ion charges always cancel. We have a -1 and a +2, and what that means is that you need 2 fluorines, or 2 fluorides in this case. And fluoride has the U before the O. Fluoride, and that's the fluoride ion, this is the magnesium ion, and when you name this compound, it will just be magnesium fluoride, and it will have the following formula: MgF2. And for ionic compounds, the names are always just the names of the ions. So this compound is called magnesium fluoride. And the only way that we know that there's a 2 in an ionic compound is because the ion charges always cancel. So if you have a 2 plus and a 1 minus, it just means you need 2 of the minuses to balance the +2. Okay. Now a second example. Let's again look at magnesium ion, and this time we'll pair it with phosphate. And this time, again, to make the ion charges cancel out, we're going to have to find some way to make the positives and the negatives cancel out. You can see that both of these numbers are factors in the number 6. In fact, if we do 3 of the +2s, and 2 of the -3s, where the parentheses and the 2 mean there are 2 phosphates, and the 3 means that there are 3 magnesiums. Magnesium 2 plus, magnesium 2 plus, magnesium 2 plus, phosphate 3 minus, excuse me, that's a scribble out, 3 minus, phosphate 3 minus. So a number of things about this example. One is the charges do cancel. We have +6 for 3 magnesium ions. We have -6 for 2 phosphate ions. That's why this is the formula here. Next thing, this is named magnesium phosphate. There are no number prefixes here. Let's see what else. Oh, so this compound this ionic compound is made up of 5 total ions. Three of the magnesium ion and 2 of the phosphate ion. So that's 5 total. Okay. 3. This time, we're going to look at FeCl2 versus FeCl3. The point being that iron can have 2 possible charges. And if you know the charge on the chloride ion, Cl is Cl minus, then we know that this one has to be Fe2 plus. And the iron here must be iron 3 plus. So this compound is going to be named iron, Roman numeral in parentheses 2 chloride. And this one's going to be iron 3 chloride. Like so. Again, these numbers do show up because they're in the name of the ions, and we need them. We need these 2 compounds to have different names because they have different formulas, and the charge is what's in parentheses in capital Roman numerals. Now, for ionic compounds, there are no molecules. So the term molecules or molecule should not refer to a sodium chloride or any ionic compound. The proper term is a formula unit. And a formula unit is another way of thinking of the smallest ratio of the ions. In an ionic compound, okay? And for example, when you think sodium chloride, this is the formula unit, and you can still call it is a compound because it's got more than one element, but it is a formula unit for sodium chloride. And that's because it's the simplest way of thinking of a picture like any one of these down here, where this one shows a ball and stick model connected, so sodium and chloride ions, and there's no just one sodium and one chloride ion hanging out in space. They're in this what's called a lattice, and so if we were to say sodium chloride, etc., then the simplest version would say there are just as many sodiums as chlorides, and therefore think of this as the empirical formula, if you will, or the simplest formula. And then this is what's called a space-filling model, and then you can also think of something called the unit cell, where you look at one particular chloride and then how many sodiums are around it. These are all 3-dimensional pictures of sodium chloride, and they all represent what we think of when we think of sodium and chloride. Sodium chloride, the ionic compound. So all of these pictures have as their simplest formula, or their formula unit, NaCl. Now let's practice some nomenclature of ionic compounds. It is always the name of the cation followed by the name of the anion. Here we have potassium chloride, because it's the potassium ion. Potassium iodide, Ki. Potassium iodide. Those are potassium, one word, space, iodide is the name of the I- ion. Magnesium is a metal. That's going to be the cation. This is the carbonate ion. Here we have calcium hydroxide. and here. So important to think about. We may not know necessarily what this is or what it's made up of, or how, how do we split this up? Well, we recognize the sodium ion, and we know that we have two of them. So two of them is +2. So whatever is left must be the anion, and it must have a 2- charge. Ionic compounds in this course always split up into two types of ions, one positive type and one negative type. And then from there, we know this is the sodium ion, so we call it sodium. This is on our nomenclature list. This is dichromate. And we just have to memorize that. Here, we just did this on the last page. I'll leave that as a companion problem for you to name those. And on this whole page, we have more practice for you.